Hey, welcome to the Explainer. Ever look at a PC spec sheet and feel like you're drowning in an alphabet soup of acronyms? Well, you are in the right place. Today we're going to decode all those essential acronyms so you have a really clear picture of what's going on inside your machine, especially if you're jumping into IT or computer science.
So here's how we're going to tackle this. We're basically going to do a virtual PC build, right from scratch. We'll start with the motherboard, then the brain, the memory, and so on. That way, you can see how all these pieces with their crazy acronyms actually click together to make a working computer.
Okay, let's dive right in. Every PC build starts with the motherboard. You have to. Think of it as the central nervous system of your computer. It's the one component that everything else plugs into, allowing all the different parts to talk to each other.
I mean, just look at this thing. It really does look like a city map, doesn't it? You've got these specific zones for the processor, for your memory, for all your expansion cards, and they're all connected by these intricate little lines. And the board itself, this physical foundation, well, that's our very first acronym.
Right, so that board is called a PCB, or printed circuit board. It's basically layers of fiberglass and copper all sandwiched together. And those copper lines, those are the highways that data and power zip across to connect everything we're about to install. And just like real highways, the designs have gotten a lot faster over the years.
Now, speaking of highways, let's talk about expansion slots. For a long time, PCI was the king. This was the slot you'd use for your sound card, your network card, pretty much anything that wasn't already built into the motherboard. But, technology marches on. Components got way faster, and pretty soon, PCI just couldn't keep up. It became a serious bottleneck.
And that's where PCI or PCI Express comes in. This was a total game changer, and this slide nails the reason why. Think about it. The old PCI was like a single-lane country road. Every device had to share it, wait their turn, total traffic jam. PCI? It's like giving every single component its own private multi-lane superhighway directly to the system's core.
And what's cool is that these PCIe highways come in different sizes, kind of like roads with different numbers of lanes. That little X1 slot, perfect for something that doesn't need much data, like a basic Wi-Fi card. But that big, long X16 slot, that's the 16-lane superhighway reserved for the most data-hungry component of all, your graphics card.
So before PCI completely took over, there was this interesting little detour called AGP, the Accelerated Graphics Port. It was designed for one thing and one thing only, graphics cards. It gave them a faster, dedicated connection than the old PCI slots. It was a decent stopgap, but PCI was just so much more versatile and eventually so much faster that AGP pretty much faded into history.
Okay, motherboard's in place. Let's get to the next major step in our build. We're installing the CPU, the central processing unit. This little chip right here is the brain of the entire operation. It's where all the actual thinking gets done.
So the CPU itself is this incredible piece of engineering that slots right into a very specific socket on the motherboard. But what's inside this chip? What's the core part that does all the computing?
Well, that would be the ALU, the Arithmetic Logic Unit. This is the engine room of the CPU. It's the part that does the actual math, the adding, subtracting, comparing, all the basic logical steps. Billions of them, every single second. But how it gets its instructions, the language it speaks, that's where things get really interesting.
And that brings us to this huge fork in the road when it comes to CPU design, CISC versus RISC. So CISC, which you'll find in basically every desktop and laptop, is all about complex instructions. One command can trigger a whole series of actions. RISC, on the other hand, is what's in your phone. It breaks everything down into super simple, lightning-fast instructions. Two different philosophies, both aiming for pure speed. Okay, so our PC has a brain. But a brain needs a desk, right? A workbench to spread out its current projects? That's exactly what RAM is for. And yep, it's got its own set of important acronyms.
Your main system memory is called DRAM, or dynamic RAM. When you open a program, it's loaded from your storage drive onto this super fast workbench. It's called dynamic because it's constantly refreshing itself to hold on to the data. But the key thing to remember is that it's volatile. As soon as you cut the power, boof, everything on that workbench is gone. Okay, so if DRAM is the big workbench, think of SRAM or static RAM as a small, super-organized tool tray sitting right next to the CPU. We call this CPU cache. It's way faster and way more expensive than DRAM, so you only get a tiny bit of it. But it holds the data the CPU needs right now, making everything feel incredibly snappy. And then you've got VRAM, which stands for video RAM. This is a perfect example of specialized hardware.
This memory lives exclusively on your graphics card. Its one and only job is to handle all the visual stuff, textures, frames, you name it. This frees up your main DRAM to focus on helping the CPU with everything else.
All right, our build is coming along. We've got the brain, we've got the workbench. Now we need the library, the long-term storage for all our files, programs, and the operating system itself. The stuff that needs to stick around when you turn the power off.
For the longest time, the standard connector for drives was SATA. It's like a reliable family car. It gets the job done. But then came NVMe. This isn't just a new connector, it's a whole new language designed for modern solid-state drives. Instead of using the old, slower route, it hops directly onto that super-fast PCIe highway we talked about. The difference? It's like going from that family car to a Formula One race car. This speed is just on another level.
So what if one drive isn't enough for you? Maybe you need more speed, or maybe you're just paranoid about a drive failing and losing all your precious data. What do? Well, that's where RAID comes in. It stands for Redundant Array of Independent Disks, and it's a clever way to group multiple physical drives together so your computer sees them as just one single unit.
Now, RAID isn't just one thing. It comes in different levels, and each one is a trade-off between speed and safety. You've got RAID 0, which is pure speed. It stripes your data across 2 drives, basically doubling your performance. The catch? If one drive dies, you lose everything. High risk, high reward. Then there's RAID 1, which is all about safety. It just mirrors everything from one drive to a second one. Total redundancy. And then you have options like RAID 5, which tries to give you the best of both worlds, a balance of speed and protection using a clever system called parity.
All right, look at that. Our virtual PC is pretty much built. We've got the motherboard, the CPU, the memory, the storage, but right now it's just a fancy, silent box of parts. Let's give it the spark of life.
And that spark starts with the PSU, the power supply unit. This thing is the unsung hero of every single PC. It does the critical job of taking that dangerous AC power from your wall outlet and converting it into the clean, stable DC power that all your delicate components actually run on. But just having power isn't enough.
So, you hit the power button, the fans spin up. But now what? How does the computer actually know what to do next? How does it wake up and find the operating system? That's the job of the firmware. It's the very first piece of software that runs, bridging the gap between the physical hardware and your operating system.
For decades, the standard was BIOS. You've probably seen it, that old-school, text-based blue screen. It worked, but it was ancient. Today, virtually every new machine uses its successor, UEFI. And it's a massive upgrade. You get a nice graphical interface with mouse support, you can use huge hard drives, and most importantly, it's way more secure.
And this is really the killer feature. This diagram shows how UEFI Secure Boot works. The old BIOS would just try to boot whatever it found first. That left a huge opening for malware to sneak in before your antivirus could even load. UEFI is smarter. It checks for a digital signature to make sure the bootloader is legit and hasn't been tampered with. It's a simple but powerful layer of security.
And that's it. Our virtual PC is built. Think about it. We started with a bare board, and just by understanding a handful of key acronyms, PCB, PCIe, ALU, DRAM, NVMe, and UEFI, we've put together a complete functional machine that's ready to boot up.
You know, this whole journey shows a clear trend, moving from separate parts to more integrated systems. We already saw the memory controller, which used to be on the motherboard, get pulled right inside the CPU for a massive speed boost. So that leaves us with a final question to chew on. What's next? What other part of the motherboard do you think will get integrated into the CPU to make things even faster and more efficient? It's a fun thing to think about. Thanks for joining me on this explainer.